session from Indiana University, Bloomington. So Larry Moss is our distinguished speaker this afternoon. Larry, welcome to us.
Thank you. Thanks. It's a real pleasure to be here. I feel sad that I'm not there in person because I attended some of the talks yesterday, and I saw all of the great talks at both of meetings. I know that I'm speaking for two meetings here, and I feel sad that I'm unable to be there and see that it's a very exciting time. And I also see that I'm the last speaker of the day, so I should try to let you go to have dinner soon. Um, is everything okay here? So I see a room with people in it, and
Yes, it's us.
that's you all. And then I see a kind of a top-down view of basically only Ruzanka's head in my. I see one of the top down. Yeah, that's okay.
Maybe you do some magic so that Larry will see better all of us.
I do see all of you in the third window. I don't know if you see. Yeah, you probably can't see what I see, but um, I can see myself in that second window.
See over there the screen.
Oh yeah, no, I see the screen. Yeah. And in fact, I see you're standing up. Hi. Okay. Okay, shall I get going?
Just wait a second, Larry.
Yep. I wait as long as you want. Yep.
To see whether we can get a better view of you.
Oh no, I'm good. I see just fine. Really, I do. I see the amphitheater. It's got three kind of long rows, very long, and the one in the middle has four seats. So I definitely see it.
Okay, once again, I'm very happy to introduce Larry Most as our distinguished speaker this afternoon. And he is a keynote speaker for both sessions for mathematical computational linguistics and for the meeting of the group on verification. So Larry, welcome with your talk.
Okay, shall I go ahead?
Yes,
yeah.
Welcome with your talk.
Thank you. Okay, so here's the very big, so this is more of a big picture talk than a very fine detail. So mostly I'm going to be talking about many different areas and what's been done and try to advertise a big area as a whole rather than little pieces. So the program of natural logic that I want to get across to both communities today is to try to think about natural language inference, but in the natural language itself, as opposed to translating it into any other logical system. So it's to try to see how much of natural language inference, and inference really means what follows from what, can be done in natural language with a minimum of translation or a minimum of any, with trying to stay as close as possible to what a linguist would call the surface, which is like not using any kind of representation unless you really have to do it. I would like to think about reworking logic to rework logic in the light of computational semantics. That's not something I'm going to talk about today, but what I will talk about is logical systems, because that I think the proof theory community might find interesting. And in fact, there is already some proof theoretic work related to the things I'm talking about that I'll mention. It's to try to show that a lot of what we do in natural language inference can be done in very small logical systems that are decidable, and to look at the algorithms to program them, to have them running on a computer, and to see how they do against things like large language models. And then finally, what I really would like to do is to be very mathematical about everything, as opposed to people who are using like large language models to do inference and answer questions, and to really make connections to mathematical logic and theoretical computer science and everything, including proof theory. Usually when I give a talk like this, I'm happier to have people interrupt me with questions. And I don't know if how easy that is with Zoom. I mean, I definitely don't have I could put a chat on my laptop that's next to me here. But if anybody really would like to ask a question, it would be great to do that, and I would welcome you to do it. And if it's too much and I don't get to finish the talk, well, maybe that's fine too. What I want to talk about today are three kinds of things. First of all, extended forms of syllogistic logic, then monotonicity calculi. So I'll explain what all these things mean. And finally, how everything works in practice. So like some of the talks that I saw yesterday, this talk has an in practice kind of aspect that I'll get to at the end. Here's a map of a lot of logical systems. So every point in the map is a logical system. And for people like in proof theory, you might find it interesting that there are so many logical systems. I'm obviously not going to talk about many of them at all today. I'm going to talk about actually two or three, um, and not even going to do the main facts about them. Let me put this over. Yeah, let me tell you what they are. So there are three. Oops. There are three lines here. This is that I named after famous people. So this is the line of Aristotle, which roughly speaking corresponds to syllogistic proof system. So there's a definition of what it means to be a syllogistic proof system. And something that's formulated in a syllogistic way is kind of below this line that I'm calling Aristotle. The line for Peano and Frege is a line of first order logic. So everything that's to the right of that line is something we could express in first order logic. And first order logic, I don't know why this is keep flipping around, but is the top. FOL is the first order logic. And finally, the line of Church and Turing is the line of decidable and undecidable logical systems. So as you know, first order logic is undecidable, and even an interesting fragment, the FO2 is two variable fragment with a little bit of extra stuff becomes undecidable. That's interesting. The FO is not of linguistic interest, but the other ones are. So starting at the bottom, the system A is actually a subsystem of what Aristotle was doing. And I will go through what that system is in a minute. In that system, the only thing you could say is like all dogs are animals. All X are Y. That's all you can do. The S above that is actually Aristotle's syllogistic. Then as you go up, the R adds relation symbols. So this is something that's famously not part of Aristotelian syllogistics. So you could do something like all dogs see a cat. So you have a word like see, so it's a verb, and verbs will be interpreted as relations. So it's a relational system. And then if you add more stuff, for example, the star, you add comparative adjectives. Um, the R is also going to involve relative clauses, as we'll see. The daggers are so the systems that have this dagger, like S dagger, and above it R dagger with a star, all this kind of stuff. The dagger has to do with negation. So negation is going to be an interesting kind of thing in all these systems. For an example of a system that's not first order, it would be actually the Aristotelian syllogism, where I add comparison of sizes of sets. So something like there's more students than professors in the room. So more students than professors, something we can't even say in first order logic. And so if it comes time to do logic about this, usually the logician says, well, you can't really do it. You're not going to get an axiom system for it. But the message of this part of the talk, and actually of the whole map, is that if you have a very weak system, you often can get full, nice axiom systems for all kinds of logical things if you don't put too much in it. As soon as you put everything that's first order logic, it's not going to be nice and axiomatizable typically, but for small things, you definitely can do it. So here's the very bottom. So this is the simplest logic in the world. So the simplest logic in the world starts as a trivial kind of syntax. We have nouns, so nouns are just like variables here, and the sentences are of the form all P or Q, where the P and the Q are nouns, and that's it. So there's no anything else, no quantifiers, no conjunction and disjunction, no anything really. This is it. And now we have a semantics. So the semantics is a trivial semantics. So the semantics is just a set. A model consists of a set together with interpretations of the nouns, and those interpretations are subsets. And then we'll just say that directly, without translating it, that's the point, is that the model satisfies all P or Q means that the meaning of P in the model is a subset of Q in the model. So, I mean, so I have a lot of um, educational material. So if anybody's interested in teaching logic with this, I have a whole lot where I use this as the first thing to teach people in logic is the all logic with the completeness theorem that I'll kind of wave my hand at. So, I mean, here's an idea. Here's a model that's got the points in it are 8 points, 1 through 8, or they could be names of people or animals, whatever you like. Then you interpret the nouns like A, X, and Y, by various sets. And then the model either satisfies or it doesn't satisfy these sentences. And then we have, since this is a real semantics, we have semantic consequence. So a model satisfies a set of sentences, and that's what this capital Greek letter gamma is. So it satisfies a set of sentences if and only if it satisfies each sentence in the set. And then we have semantic consequence, which is just as you know from logic, every model of everything in here is also a model of the consequence. It's all semantics. And now here's the proof system that goes with it. So the proof system has as an axiom all P are P, because that's always true in every model, no matter what the interpretation of P is. It's a subset of itself. And then we have the medieval rule Barbara. This is the most famous rule in logic for 1500 years. All P are N and all N are Q, then all P are Q. And that's the proof system. So the proof system is completely easy, but I think before this subject got off the ground, I don't know that anybody ever isolated this as the like key fragment and looked at what would completeness be for this. So a proof tree is just a tree that you build out of these. So I think maybe half the people here are in proof theory, so you know what a proof tree is. So it looks like this. This is a proof tree. Here's a set of assumptions. Here's a conclusion, and here's a proof tree. And all it means is that at every interior node, we're using Barbara. All A or B, all B or D. It follows that all A or D. And for nothing, for free, you get all A or A. I mean, you don't need any. There's nothing above that. That counts as a proof rule with no assumptions, and it's complete. So this is the completeness theorem. I think it's the simplest completeness theorem in logic. And it's actually so easy that if I just tell you that it's easy, you probably can go off and prove it. And so I think I won't take the time to do this, but really the proof is something that you can teach people. Um, so my students are math students who never really saw proofs in high school math. And of course, it's not that easy to do. I mean, you need to deal with notation and definitions and the mix of syntax and semantics. But it is possible to do it. You really can teach people this and give them homework. And I have a lot of materials if anybody wants them. And you can go on and add all the rest of it. So here's if you add the word sum, like in classical syllogistic logic. You can add the words like some P or Q, and here's the semantics, just what you'd expect. And the proof system has the axiom, that's all P or P. It has Barbara. It has the conversion rule from the classical logic. It has this rule, which is not part of the classical logic, because in the classical syllogistic, you don't repeat the same noun twice. And it has this rule, which is the connection of all and some. That's Dari. And then this is a it's complete, right? So I mean this is an example of what a deduction looks like. Let me breeze ahead here. You can also add complements where things become really interesting. So if you add complements and take it to be the classical complement. So let's say if I put smoker in for P, then smoker with a bar over it would be like a non-smoker. And you'd interpret the non-smoker by the set of things that are not in the smoker set. So this is the classical. I mean, it's like the law of excluded middle is kind of built in here. So if you're interested in things like intuitionistic logic, you might say, well, I don't really like this. Give me a better semantics. The better semantics is completely fine. I'm not actually committed to this being the semantics of the natural language. What I'm really committed to is the idea that there is a semantics, and once we have a semantics, we should try to think about what the complete proof system is. If you don't like this semantics, if you prefer to have a different one, you should propose a different one and get the completeness theorem. And then you would see what your semantics is kind of demanding of you and what it's not demanding of you. And in this case, so this is what we get. We get this is it, and I'll show you the rules in a minute. Now the system S that I had on the previous slide is just these ones here. If you have the dagger, you can replace things like well, I didn't mention the word no before, but we could actually have no. So saying no P or Q is like saying all P are not Q. All P's are not Q's. And you can say that and work with that. And in the S dagger one, you also have full negation, even on the head noun of a sentence, some non-P or non-Q. Now that's pretty rare in natural language. To be the head noun of a sentence and negated it sounds actually kind of weird. But this is what the logic delivers you. And then, the logical system, well, I had this system up before, and then so here's what you get for the complete theory. You get the ones on top, plus things that have to do with vacuous quantifiers. Like if all Q are non-Q, if I say all smokers in the room are non-smokers, then in the semantics, it implies that there are no smokers at all. If I say all smokers are non-smokers, it means that there are none. And that means that all smokers are P, no matter what P is. So this is only for the like mathematical kind of reasoning. Right in the real world, nobody would say this. So again, it's very good to think about how pragmatics should enter into all this. And I'll have one thing to say about this a little bit later. This is even worse in some way. If I say all non-smokers are smokers, it actually means that everybody is a smoker. So that's even more unusual. But you get this as a consequence. This one is it's easier to see if I change it to the word no. So if I say no P's are Q's, it follows that no Q's are P's. You also have the ability to have contradictions in this language. So if I say some P are not P, that's not satisfiable. So that means that in the semantics, no model satisfies it. So that means every model which does satisfy it satisfies everything. And that means we have the law of ex falso, the ex falso quod libet. From a contradiction, the reasoner can have anything she wants. So that's what this means in Latin. And this is actually a little bit different than reductio. So reductio means that you're negating a premise, right? So it's different. And so one of the things that happens when you do a very tiny logical system like the ones in this family, every choice you make kind of reverberates with philosophical discussions across the ages. And in fact, the difference between reductio and ex falso is a live issue here. Like, can you get by with one and not the other? Does one imply the other? When and stuff like that. So all of these very small logics are ways to address this kind of a question. Now, what about this one? This is my favorite example. So if you have seen some of this talk, I apologize, and uh, I'll try to show a lot of new things. But if you haven't seen it, supposing I tell you as an assumption, all skunks are mammals. So all skunks are mammals. Let's say you don't know the English word skunk, and you don't know whether it's a mammal or not. Maybe it's a bird or something. And let's see, does it follow? All who respect all skunks, fear all who respect all mammals. Now I'm not in the room, but I can kind of see the room. So how many of you think that this follows? You don't have to. How many of you think it does follow, and how many of you think doesn't follow? So follow means everybody who believes the top line should believe the bottom. That's intuitively right. And in the formal details, it means every model of the sentence on top is also a model of every model of every model of the top sentence is also a model of the bottom one. So how many of you think it follows? Nobody, nobody that I can see. I can only see a few of you. And how about the bottom? How about no, how many you? How many of you think it doesn't follow? That it shouldn't follow, and it looks wrong. Come on, I can see you guys. Nobody's raising your hand. Okay, am I right that nobody's raising their hand? I think I am. Okay, there's a few people. Okay, so the two people, there were two people on the side who did. So did you guys raise your hand for follow or not follow? Not follow. Okay, thank you very much for expressing a point of view. Really, really and truly. It's my favorite thing to get people to see about this stuff. So in fact, this one actually does follow. Let me show you why. If I say all skunks are mammals, then everybody who respects all mammals respects all skunks. So that actually follows. So it follows intuitively. If all skunks are mammals, then if you respect all mammals, then a fortiori, you respect all skunks. And notice that the red and the blue have switched places. So that's what's called antitone. So I'll have something to say about that in a few minutes. So that follows, and that means I can use the principle again. So this is why it's difficult, is I'm using the same principle, which you didn't even know, twice. So if I tell you, oops, oh, if I tell you all skunks are mammals, then it follows all who respect all mammals respect all skunks. And then it follows again. So I took this off by mistake. It follows again that all who fear all of the red ones fear all of the blue ones. And so that it follows. It actually does follow by using the same principle twice. And I'll show you this again in a second. So here's how you would do a logic that has all, like this is what Aristotle was doing, verbs, which Aristotle didn't quite do, and relative clauses. So I'll show you this in a minute. So it starts with nouns and verbs, and you make what are called terms. So terms is from term logic. So term logic is basically the generalization of syllogistic logic, where the items, the syntactic items, denote sets. So nouns are terms, and if you have a verb like respect, then and a term, then like respect all skunks is a term. But it's also recursive, so terms can be arbitrarily large. And the sentences in this particular logic are just all X or Y, where the X and the Y could be any terms. They don't have to be basic nouns. They could be any terms. So for example, if these are my nouns, dogs, cats, birds, and so on, and the R denotes transitive verbs. That means verbs that take a direct object. Then some of the terms might be something like see all dogs, respect all, see all dogs, right? I mean, you have a verb, the word all, and then another term. And you would read this with this is called a relative pronoun in English, who. So this would be like respect all who see all dogs. And this is love all who, respect all who see all dogs. You read this in English by sticking in the relative pronoun. And then you could say, well, and then I'm not going to go through the semantics. The semantics is we interpret the word love or see or respect by a verb, by a two-place by a relation, just like we would in like modal logic. So respect would be a relation on the world where the first one respects the second one. And now here's the logic would have the axiom and Barbara, as we saw before, and would also have this rule anti. So if all y's are x's, then all who love all x's love all y's. You know, all who see all x's see all y's, etc. And no matter what the verb is. And so now you can prove it in this logical system. So if all skunks are mammals, then so skunk and mammal are my two terms. Then it follows that all who love all mammals love all skunks. So that's an application of this anti-rule. But then it follows it again, all who hate all who love all skunks hate all who love all mammals. And you could prove that this is the complete logic of this and teach people this. This here is this logic R here. So there's a whole lot more you could do with syllogistic logics, and I don't want to take my whole talk doing this. In fact, I would like this to be a short part of the whole thing. But let me tell you some other things you can do. You could do logic that's beyond syllogistic logic, so beyond this Aristotle border, by coming up with variables. So variables are what you need in the classical logic, and the way variables work here is pretty much the same. You don't really have you don't have all the issues about substitution and binding because the variables are only used in the proof trees. So let me show you what I mean. So this is if I tell you all keys are old items, then we could infer that everybody who owns a key owns an old item. And this I'm going to translate it like this. I could write it in English. So there's various kind of rules like this is the rules that you know from logic, like eliminate the the universal quantifier, introduce the I here. Introduce the existential quantifier. You have just like the usual stuff in proof theory, and you could, based on hypothetical things, prove everyone who owns a key owns an old item. Now, the first person to do something like this was, I think, Fitch. So this is a proof in the Fitch style. It's the same proof, but just written in the style of a Fitch proof. And Fitch himself, okay, in 1973, wrote a paper called Natural Deduction Rules for English. And this is So I apologize for anybody who's offended by this example. This is from his 73 paper. This is 50 years ago. John is a man, and any woman is a mystery to any man. So this is kind of interesting because he was worried about this word any, which is which, as you know, is problematic. I mean, so that he was interested in it. And in fact, I don't think he completely got it right, but he at least raised the issue in some sense. And so he said, well, let's think of a variable Jane, introduce a variable Jane, and assume that Jane is a woman. And then you do whatever it takes with your rules about any to prove that Jane is a mystery to John. And then you would infer by a rule that he called any introduction that any woman is a mystery to John. So he was interested in formulating rules like this. Now he, interestingly enough, didn't have semantics. So he did this in 73 when Montague was actually working, and he and Montague kind of crossed paths. So he introduced the proof theory for English, and Montague introduced the semantics for English in a way that's totally related to what I was doing. But they didn't each do the other's thing. They could have. I mean, Montague could have actually said, "Oh, now that I have the semantics, I could think about proof theory, and what is the complete proof theory of my intentional system, let's say." And Fitch could have said, "Well, I have this idea that there should be natural deduction rules, but I don't have any reason to think that they're sound." He didn't have any semantics, so that's all. The connection is interesting. So here's a review of what I was doing. There's all this kind of logical systems. It's connected to computational complexity, which I'm definitely not going to talk about here today. Like as you go up in the chart, you go from things that are, the logic that I showed you, the A logic is in polynomial time. All these are easy, and then you go up and add more linguistic stuff, and it's higher complexity. The yellows are the exponential time, so all these fragments are in exponential time, and then undecidable is given by that line here. Let me tell you some things that I'm not going to talk about, but if anybody wants me to talk about or wants to ask me about, I'm happy to talk about it. There's a lot more on the relational syllogistic logics in connection with, especially with things that look more like modal logic. There's a whole lot of work about reasoning about the sizes of sets. So if I tell you, well, most X are Y and most Y are Z, should it follow that most X are Z? So this one, everybody who raised their hand saying no before should say no for sure, because it definitely doesn't follow. But there are some rules that are sound, like if most X's are Y's and all X are and all Y are Z, okay, most X are Y and all Y are Z, then certainly most X are Z. Then you might ask, well, what do we have to do to Aristotle's system to get it to be complete if I add something like most? This becomes interesting and combinatorially interesting. I have a logic for definite descriptions, which is also, so definite descriptions are interesting because, they sometimes fail to denote, like in the classical example of the King of France, the present King of France. It doesn't denote, and then you might say, well, how can you do logic with this? I mean, if you could do it the way Russell did it, you could do it the way Strawson was thinking about it, and with a small logical system like this, again, every choice makes a difference in the formalism. So you can definitely add definite descriptions and names, interestingly enough, to the logical systems. The paper that I did most recently, actually, which was in some sense finished yesterday, was a logic that had syllogistic logic, but with and or on the level of the nouns. And so this is connected to description logics. So in computer science, these are something that's used in knowledge representation and parts of AI, especially the symbolic AI. So these logics, the logics that are natural logics that have the and the or are fairly close to description logics. And the proofs of the completeness go via lattice theory. So if you're interested in any of those, definitely ask me. And in fact, I think it's probably a good time for me to stop and ask for questions about this before I go to a totally different subject. So would anybody like to ask anything? No. Okay.
Can you hear me?
Yeah, not quite, but close. Go ahead. Speak a little bit loudly.
So in your proof systems, you showed if you go into really old papers, you see, for instance, that implication is written as a subset or superset symbol.
Yeah.
And in your previous slides, you mentioned like this set denotation. So the term denotes a set.
Yeah.
Is this a coincidence that that if you look at it like that, this transitivity, etc., are also properties that hold implication?
Negation flips things, though. I mean, yeah. So I said, well, are you finished with your question? Because I'm not sure I understood it as a question.
Yeah,
What?
yeah. Here's the question mark. Yes, thanks.
So what the question is, what about negation being, let me see, this is the, do you mean this particular step would, this is the only time I really mentioned negation. Let me say, I put down the semantics of everything using sets because that's the most basic thing to do. But again, if you prefer something more complicated, then you definitely can play the same game and you put down any semantics you like. Like, for example, if you don't like the idea that all P or P is always true, like when P is empty, people don't often like this. So if you want to do like Aristotle basically did, uh, assuming that you only like all X are X when the meaning of X is not empty. Let's say you like that better. And most people actually like that better. Then you can just change. You would change the logic, and it's not. It's a good exercise to change the completeness theorem, and to change the rules and the semantics and the get the completeness theorem for all the way Aristotle did it. Does this help you? Or
Yes. Yes.
okay,
Thanks.
okay, sure. Thank you. I said that this talk would have three parts, and so this was the first part. And the second part I want to introduce with a video. So this is a 3-minute video here. So I hope that if this thing should actually have the sound going. So tell me if the sound goes when I start this. Can you hear? Can you answer a question? Can you hear that? Oops.
Yes. Yes.
Okay, let me start it again. So the important thing for you all is that the words are made up in this video. How can you answer a question involving words that you don't know? How can a computer do it? We'll see how, and we'll see how math enters in. Here's a sentence with some made-up words.
All the glogglfish swifferate past a yub.
And now let's ask.
Do all striped beglogglfish swim past a yub?
To answer, let's take an ocean voyage to meet a beglogglfish. Some beglogglfish are striped. We put all this information in a scale. Up means more general, and down means more specific. They swim and they swifferate. Here is the scale of the verbs move, swim, and swifferate. Supposing I tell you about a picture that
All the glogglfish swim.
what would you be committed to? Here are the sentences that you would accept. These are what you infer from my statement. The pattern is, on the left, we move down the scale. On the right, we move up. When we change the word
All,
to,
some,
the pattern changes. And when we use the word,
no,
the inference is different yet again. It's down both times. And when we start to look at other sentences and other words, we see the same kind of patterns all over the place. The same happens with numbers. Let's look for a second at 41 minus 32. The arrows tell us that to make 41 minus 32 bigger, we can either move 41 up or 32 down. Let's put numbers and language together. In mathematics, we put things which are similar under the same conceptual roof in order to study them together. That roof is called a preorder. It's what we are calling a scale. We think of a sentence like, all beglogglfish swim, to be the all function applied to a noun and a verb input. The language of preorders allows us to talk about increasing and decreasing functions. Let's go back and answer the question that we posed at the beginning. What you do and what a computer could do can be studied as an application of mathematics to everyday language. Oh, I don't know what this is doing here. Yeah, sorry about that. Okay, so what I'm going to try to do is to show a little bit about how the formalism works in doing this and how this is ultimately connected to kind of computational linguistics. So this is a fairly condensed version of something that would take like 2 talks to really do. So, but I'm aiming this kind of at people who have seen like proof theory a little bit. So this is the rules of what's called CCG, or combinatory categorical grammar. So this is a little bit like, so you should think about the slashes as like arrows, like an implication arrow in logic, but it has a direction because word order matters. So these 2 rules have to do with function application. So if you think about this as like a function from y to x, this arrow, then if you have it's like modus ponens or function application, and it's called function application. So this is a function application kind of thing, or modus ponens. This is the same thing, but there's a left and right distinction, right? This is x looking to the right for its argument. The T is a type raising. So type raising, if you have never seen this, you might know this from, for example, the proof of the completeness of the proof of a stone representation theorem. So you're identifying a point with its principal ultrafilter. This is one way that you might have seen this if you have never seen this kind of a move. This is another type raising. This is function composition, right? A function from x to y and a function from y to z composed to be a function from x to z. And this is composition in the other way. Now, in this kind of grammar, every word has a what's called a syntactic category. So a word like every or some looks to the right in English for a noun and becomes a noun phrase. So I'll look at if I put every next to cat, I would get every cat, and that would be a noun phrase. And then what counts as a sentence here is if there's a proof. And a proof here means a proof tree that the leaves are labeled with stuff from this lexicon. So lexicon are like kind of my assumptions about the words. So this assumption here that Fido is a noun phrase, which is kind of given to me in the here's chaste. This is what a verb looks like in this kind of setting. And then so if I want to put together Fido and chaste with Fido coming first, I would raise Fido from the noun phrase type to this type, and then I would combine it with this one, and I would get Fido chased. And then so I really would like to get the sentence, every cat that Fido chased ran. And this would be a proof that it is such in this system. Now, the idea of having these arrows here is I really would like to know this, which is the kind of semantic part of the whole thing. So semantics is the meaning, and the meaning is in blue in all of this, and the syntax is in red. So the red here means just in the syntax, nothing to do with the meaning. The first step in giving you a nice account of the meaning is to trade in the syntactic like slashes left and right to the semantic arrows, and these are like function types in the typed lambda calculus. And then, but what we really would like is to decorate this with arrows here like this. So if I say every cat that Fido chased ran, I would like to know that, for example, it's down in the word cat. So if I tell you every cat that Fido chased ran, and I know from language that, for example, a black cat is a cat. So black cat would be less than cat. Then it follows that every black cat that Fido chased ran. So this sentence, every cat that Fido chased ran, is down in the word ran. It's up in the word, sorry, it's down in the word cat. It's up in the word ran. So something that a speaker of English knows is that running is a form of moving. So running is less than moving. And if I tell you that every cat that Fido chased ran, it follows that every cat that Fido chased moved. I would like all of this kind of inference. So this is inference without really grammar in a way, because I would like to get this to work on things that don't come with the grammar, but just use the arrows. So that if you have a computational system that could put in the arrows for you by a computer in a fast way, and you have a lot of basic facts, like, for example, black cats are cats, running is a form of moving, stuff like that. Fido is a dog. If you have some kind of assumptions, then you should be able to do inference on a computer. That's without translating into first order logic. So that's what's going on with all of this. So here's another one. If I tell you, well, if I want to think about Fido chased some cat and no armadillo. So an armadillo is a small kind of thing that lives in Texas with a hard shell. Fido chased some cat and no armadillo. It should be down in armadillo, up in cat, and chased, you should not be able to go either up or down. So if you're combining something that's increasing like some cat and decreasing like no armadillo, then in the word chased, it's not up and it's not down. So I don't think I have time to give you examples with this. But there's this up means you can replace it by something bigger in some abstract sense that I'll mention. Down means you could replace it by something smaller in the same kind of abstract sense. And equals means you can't replace it at all. You have to stay equals. That's what it means. And so there's a bunch of semantic rules, and I'm not even really going to tell you how they are justified. But let me just say that this one is related to function application, but in a pre-ordered sense. So everything here has to be ordered, and the mathematics here is the mathematics of higher order pre-orders. So pre-orders means a set with a relation that's reflexive and transitive, and a higher order pre-order is where we might have the functions from one pre-order to another, right? The functions from one pre-order, let's say the truth value pre-order, to a noun pre-order, or the number pre-order to the verb phrase pre-order. That function set is itself a pre-order under the pointwise order. So we can talk about monotone functions and something just like in the video. And this is going to be a kind of pre-ordered version of function application. Okay, then there's type raising. There's also function composition, and there's a fairly complicated rule that I'll show you in a second, that actually is related to what Ed Keenan called the justification theorem, or what in the category of the grammar world is Hermann Hendrick's work. And then there's various forms of weakening. There's two forms of weakening in the system. So proof theoretically, this is already an interesting system, I think, and I'm still exploring it and with a postdoc proving properties of the algorithms and so on. So here's what would happen is if somebody gave me like the sentence, some dog chased no cat, I would like a system that outputs trees that are decorated with arrows. So this is this rule K that I said is a kind of a complicated rule, but notice that the arrow flips here. So that's already a sign that something interesting is going on with this. So some dog chased no cat. The rules are about the local subtrees, and the overall exercise is to what's called polarize the tree, which means you've got to put an arrow on the bottom. At every interior node, it has to match one of the rules. So this is the rule, this function application rule. And then there's this K rule, which flips the arrow from the down to the up as you go in the down direction. There's a kind of semantics to the whole thing, which has to do with higher order preorders, and there's opposites. So if you know about the Galois connections of higher ordered stuff and monads, this is it in some sense. And now I would like to move into the end of this talk where I try to show you how you how you use monotonicity and the natural logic to do inference on the computer. So this is the computational linguistics kind of thing. So there's a lot of data sets in the what's called natural language inference, and this is really probably the very first one called the Fracas data set. So it's totally obsolete now that we have data sets with a million, a billion entries and stuff like that. This one had a very small number, just I think in the small thousands. So supposing I tell you a schoolgirl with a black bag is on a crowded train. About the next sentence, does it entail the next sentence? Does it contradict the next sentence? Or is it, should say, neutral? And the second sentence is no schoolgirl is on a crowded train. So does the first one imply the second one? Does it contradict the second one? Or is it neutral? So you should all tell me that it's a contradiction. It's a contradiction. How about this one? A schoolgirl with a black bag is on a crowded train. Does it follow that a girl is on a train? Okay, so everybody would say yes. So how do you, what goes into this? You need to know, for example, that every schoolgirl is a girl. So you need to know that. You need to know that this with a black bag you can ignore. So that's like an instance of going up in a preorder. So if you have a modifier, if you drop the modifier, it goes up. And then to be on a crowded train, you're certainly on a train. So again, if you're on a crowded train, it follows that you're on a train. So you need all of this kind of monotonicity information, and then you need to put it together. In fact, the way that our stuff works is you would take the sentences like a schoolgirl with a black bag is on a crowded train, and no schoolgirl is on a crowded train. And the first thing you would do is you would put the arrows in, since we have a nice computational account of how the arrows go. And then you would well, you have various kind of rules of contradiction. So for example, you read the word, you need to know that in this case, the word is means some. Like in English, it doesn't always mean that. So sometimes the is kind of a generic every. Like if I tell you a madrigal is a form of a song, that means kind of every madrigal is basically a song. But in this case, the is not a generic. It's actually kind of an existential quantifier. And you need to know that that actually contradicts with the word no. And so that's kind of built into our system. And then you have various other things like this where you do inference, like this one here is I drop the word black, and then I'll drop the word crowded, and then I'll you very soon will see that this one contradicts the schoolgirl with the black bag, is going to contradict this one. And this is inference as you go down. So the system itself, it goes into, has various modules. So somebody would give us a bunch of premises in English. That comes from the data set. We would call a parser. So parser means it's going to do the syntactic analysis for us. Then what I showed you today, very quickly, is the arrow tagging, which means the parse doesn't come with the arrows. The parse is just giving you the grammar tree. And what we did was to give the mathematical account of the arrows and an algorithm that puts them in. And that gives me what I'm going to call polarized parses. And then there's going to be various knowledge. You'd have a knowledge base, like, for example, that a schoolgirl is a girl. A crowded train, well, you need to know that crowded, it modifies going downward, whereas some things modified without that, or even the opposite. Like if I say an alleged killer is on the loose, the alleged might even mean that the person's not a killer, like that. Then there's an inference engine, which is kind of what I hinted at the previous slide. And there's various natural logic rules, like the ones that I showed you about Barbara and a whole host of other ones from the natural logic area, and monotonicity reasoning, which means replace according to the arrows. So that's what the video was about, was monotonicity rule. And then you should be able to output whether we have an inference, a contradiction, or neutral. So on another data set, here's what we so this is old work now. We started to do this at the time that neural net parsers were actually doing very well. They were being introduced in around 2017 or 18 into this, and we were doing this work independently of all that about the same time. And our system with some extra stuff was getting about 81% accurate. The BERT system, so BERT, this is before there was large language models, there were language models. The BERT out of the box, just absolutely as soon as my students could get it running, was doing better, was doing 86%. There are a bunch of other logic systems, so we're not the only ones to do it, and I want to mention all these. So probably the most, the one connected here the most is Lasha Abzianidze's system, which is a Tableau system, and also Hitomi Yanaka's work, which goes via translation of the CCG tree directly into typed lambda calculus and then calling a theorem prover, was actually doing very well too. So I think of all of these as especially the last three, as doing the same kind of work that I'm doing, but not starting with syllogistic logic, but starting with some other logic idea. But they're all basically in the same kind of ballpark. They were doing somewhat better than us. And I actually started to do all this work not because I wanted to compete with the language models, but just because I wanted to see if it was any good. And my students sort of said, well, nobody will care what you have to say unless you can beat the language models. And of course, we weren't beating the language models at first. We at some point decided to hybridize what we're doing. So monologue means monotonicity and logic. And when we hybridized them, we did better. We raised from 81 to 85, and we were close to what this was doing. In fact, I had some people who were undergrads at the time. They were undergraduates. Now they're graduate students. They actually decided to change from CCG to what are called universal dependency parsers. And that means that they improved the arrow tagging part of the whole thing. And they also wanted to make it a better interface with neural net models. And they had things like, well, if you say John refused to dance, it follows that John refused to waltz. So dance, it should be down in the word dance here. And whereas the monologue system that I did a minute ago didn't have that kind of information about these kind of verbs. Now, what happened? This system actually is the best here. This is called universal dependencies to monotonicity, and you could get that. And this is the system is called Neuralog, which is the ending system. And this system actually does slightly better than the neural net parsers at the time. At the time, this was the best work on the data set that it was addressing. Now, with the advent of the large language models, every 6 months, these do better and better. I'm quite sure that these would do better than any system that we have, which shows the value of a massive amount of training data and things like this. So the 2,000 years of the logical tradition don't do as well as the 4 or 5 years of large language models, as it happens. So I wanted to end by just telling you kind of all about all the other work here, and these are some of my collaborators. I'll tell you a little bit about them. Here's a long list of other things that I could talk about that, if you're interested. So in some sense about monotonicity, I extended monotonicity from the work of Johan van Bentham, who did it for regular categorical grammar, to CCG. So that's what you need in order to get a running system, because categorical grammar is not really connected to anything that could be parsed on a real computer. There's an order-enriched version of the typed lambda calculus that I did with Thomas Eickart. So I think for people in proof theory, might actually find this interesting because it's a version of the typed lambda calculus with extra rules that are all about the order. We have a running system. We have 2 running systems. We have monologue and neuralog. Now, the one thing that these things have on systems like ChatGPT is that if we say something is an inference in one of our systems, like it comes with a proof. So it's not like I matched all the data and I can see that what you're saying is right. It's like our stuff actually comes with a proof, and a proof can be translated into English fairly easily. In fact, you could also use our work to generate training data for a machine learner. I mentioned stuff about the sick corpus. Let me say, we also, so all these corpora generally come with the answers to whether words are up and down or whether something follows from something else. These answers are often wrong. So we went through the sick corpus, which is about 10,000 pairs of sentences, and with a gang of people over the course of several years, did a full analysis of the 10,000 sentences and found 30% of them that we didn't agree with. And from that, and from our own disagreements with each other and trying to understand what this is about, really came to a deeper understanding of what annotation means. That means what it means to decide on this kind of stuff, and also what inference is. And I think, well, I could give a whole talk about what we learned about natural language inference by looking at 10,000 cases. And nowadays we're looking at mathematics. So especially about, so why are we looking at mathematics? We're looking at mathematics basically because a few people in our group are really interested in that, especially Valeria de Paiva. So Valeria, I think more than anybody else on this, is interested in thinking about the area of mathematical AI, about using artificial intelligence to prove mathematical theorems. And so what we would like to do is the linguistics of that enterprise. And we have some partial results about exactly how computational linguistics could enter into that work. But I think I will stop here and let you ask questions and finish your day. So thanks.
Thank you very much, Larry. It's a wonderful talk.
Okay, thank you all for coming and listening.
All sorts of questions and concerns. So please welcome with the questions to Larry.
Maybe I went too fast, and so I'm not able to ask a good question.
A bit speculative, but did you apply to legal systems? Did you try to?
Yeah. We didn't, but others do definitely try to do that. I mean, there's numerous problems with the legal reasoning, and yeah, no, we didn't. There's a conference that we started. Let me see if I can. So I think you might look at this conference called this Natural Logic Naloma's Natural Logic meets machine learning. So this is annual or every 2 years, and it's I think there might have been some papers at this meeting. This is the meeting that's closest to this work that do talk about legal reasoning. There's numerous problems with legal reasoning, which is that it's based on defaults. Oftentimes there are things which are true with defaults, or there's numerous other effects that are not part of usual semantics, and it's a very difficult thing to do. I definitely didn't do it, and I think it would be a good thing to do. You would learn a lot by doing it.
Yeah, hi Larry.
Hi.
Nice to see all this. I think you were mainly working on inferences from one sentence to another one, but in mathematics and legal reasoning and many other things, so you have very long chains of arguments where relation is not whether one sentence follows from the previous ones, but it's kind of much more.
Yeah.
Complex. So how do you think this kind of approach is generalizing those?
Yeah, let me actually, I think I need to get rid of this thing here. I wanted to show you something in the slides that I did show you. Let me put this back here. Let me show you this. In fact, everything that I did holds in the multi-step case. So for example, like here's an example. I mean, in general, all these have multi-premise cases. In fact, that's the only thing I'm interested in is the multi-premise case. And all the ones that I showed, like this is one with 1, 2, 3, 4, 5 premises, and the tree goes like this. So absolutely, oops, did I not share that?
No, so you share
Oh, Yes, I'm sorry. Let me go to Zoom and then I'm sorry. Yeah. 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 So this is this is 1, 2, 3, 4, 5 premises here. Can you see this? You see, right? The screen? Yeah. In fact, in general, everything is a multi-premise here. So the answer to you is I'm only interested in the multi-premise case.
Okay, but
The rules, mostly the rules have only 2 premises in the individual rules, but in an argument you have more than 1 premise or 2 premises.
okay, so you see no principal difference between a mathematical proof, which it has a long chain of or tree
Right.
inference.
No, yeah, no difference at all. Our stuff applies to that case. So our stuff I'm only interested in the multi-premise case. So I'm on your side. I think that's the only thing that I want to see.
Benchmarks are usually about.
The benchmarks are about like 1 premise and 1 hypothesis. And I agree. I think that's just way too limited. I totally agree with you. If it was up to me, they should be thinking about multi-premise examples. Do you agree?
I mean, of course, yeah.
Yeah,
Inference.
yeah, no, I think that what they do with the test suites are much too limited.
Yeah.
Hi, Larry. Can you hear me?
Yes. Hi.
Hi, that's good. And I vaguely remember when I read your CCG to mono paper.
Oh, okay. Okay, thanks.
Yeah. And am I right in saying that all the data are auto-generated? I mean, you mean that this data for both your system and for Word?
I think you're a little bit far from the microphone, so I can't really hear everything you're asking. So,
Microphone? Okay, that one. I see. So I'm speaking in the wrong direction.
okay.
So, am I right assuming that all the test data and the training data are auto-generated?
No, the test data
Yeah.
is always usually the test data is from some data set that we got from somebody else. So like, for example, the SICK data set or FRACAS or even this SNLI and MNLI. So the training data, the test data is from somebody else. The training data, well, the training for, the system like Monologue didn't have it's not a neural system, so it didn't really have much of a training data. What we did was, for that one, we kind of cheated. We kind of looked at what was in the data set and we added whatever lexical work we needed. So if you needed to know that a Pavarotti is a tenor, okay, that's the classic example, then we basically gave that to our system because we're not in the business of inferring that from data. So we told our system everything it would need about the basic nouns.
Okay, then I may change my question. So I'm asking this because I believe that your system for the natural logic in general can be used to generate the inference data in infinitely many ways.
Yeah, we did. We also did that with
Yeah.
Kyle Richardson. We did that too.
And
Yeah. Yeah.
so I'm interested in to what extent or
Yeah.
until what depth the LLM can solve problems. And do you have any idea about that? So if you can generate that inference data of depth 100, for example, that cannot be solved by no human being. And what happened to LLM? So that is what I'm interested in right now.
Yeah, we didn't do that. I mean, yeah, well, first of all, I think the one who did most of this, I think, is Hitomi Yanaka. So you should ask this to Hitomi. And I feel like,
yeah, I know very well.
Yeah.
Well, she just took the inference up to the depth 4.
but how depth 4? You mean 4 levels of
4 level of embeddings.
But but a human being, you never even come to 3 levels. I mean, rarely would you ever
I
even.
know, but well, I'm wondering how good is LLM?
I never did that. I have no idea,
Oh,
actually. I have no idea. I think if I was going to do this, I mean, I think we did something similar with Kyle Richardson. Um, we never did like a depth of 100, but we know that if you train, and this is actually on the BERT models, if you train them on depth 3 and 2 and 1, they're not going to do very well on depth 4. So they can't even go to the next depth very well. Now, a large language model today, I'm not sure. I can't really speculate because they're so much better that I don't really know. I don't know the answer to that. It wouldn't be
okay.
hard to find. It wouldn't be hard to run it and find it out. But
Okay, thank you very much. Thank you.
thanks for the interesting question, and to everybody else too.
Yeah, thanks. I have a question. Can you hear me okay?
Yeah, I hear you better than anybody. Yeah.
Okay. I guess there's the microphone there. Yeah, oh, that one, I see. Yeah, so you were looking at the up and down arrows for the different words. I mean, I can imagine situations where there's a complicated, maybe infinite reorder on some of the terms that you were looking at, but I'm curious also if there's anything you can say about when the word like all or some itself has degrees of gradation. Like if you imagine cardinality quantifiers, right? Like there are at least 7 instances or uncountably many or something in place of all or some. Is that something that you can also dial up and down with the preorders?
Yes, I mean definitely. That's an important point. And that was in the video too. If you had something like there are less than 6 students in the room. So let me say that. Let's say there are less than 6 students in the room. Then if I would put that in my system, the word 6 would have an up arrow. So that we definitely have built that in. So that means if I tell you that there's at less than 6 students in the room, it follows that there's less than 7. And so the pre-order of numbers is an infinite pre-order. So this exactly addresses your question. And the numbers, well, if I tell you that if I have it at least 6, the 6 would go with an up arrow. And if I have at most 6, that the most would go the other way. I hope I'm telling you the right way. If I say at least 6, yeah, sorry, if I tell you that there's at least 6, it follows that there's at least 5. And if I tell you that there's at least 6, it follows that there's, sorry, at most 6, it follows that there's at most 7. So our system works on numbers like that. Does that address your point?
Yeah, that's one part. And then I was also wondering, like the at least 6 taken as a phrase feels also like it's kind of similar to all or some. Like
Yeah, that's right. Yeah, that's right. It is. Yeah.
but with all and some, you don't have the arrows directly. Or I guess the question is, can you view all and some as having arrows where they live on this continuum of counting quantifiers?
Yeah, they do. In fact, I didn't put that on here because I didn't really do very much about it. But in fact, what you would have is actually there's an ordering on the quantifiers. So the idea of ordering extends from the nouns and the verbs to everything. So for example, if I tell you all, it follows that most. So I would have like all is less than most. Okay, or most is less than some. So if I tell you most people in the room are smokers, it follows that some people in the room are smokers. So the idea of this idea of ordering on the words extends to the quantifiers.
Thanks.
Yeah, no, in fact, that's an interesting and important thing to do. There's a lot of interesting math about this ordering in the higher type setting.
Does it connect at all to like Kiesler or others' work on uncountable quantifiers and things like that? Like it,
I mean, I know what that is. No, I would not say that it does because his work and work like that is usually on top of the first order logic. And I mean, I feel like there's a kind of like a very distant and small connection, but not much sound for all models. So, and if you want to add the quantifier uncountable many, I mean, you could. That's not a problem. But it doesn't. It's what he was doing was trying to. He got the complete theory of that quantifier, but but I don't think that any of the work that he did use any of the ideas of what we're doing or the other way around.
Okay, thank you.
Sure.
Some more questions?
Okay, I wish I could be there with you all. It's nice to see you and to be there too.
Question. So, have developed a system, automatical system with this proof system in IU Bloomington, or do you plan to do that?
Well, I mean, I think I mentioned that we have the system called Monologue. The system CCG to mono, you can find online. And if you look at my student Hai Hu, his webpage has it, and he's in Hong Kong at these days. You can get this and download it and run it. The system here from this one here called, well, it's called Neurolog. This one here, this is even the best. Neurolog, you can also find it online. I would like to get back to that kind of work of actually doing inference online on the computer. But that project and the project of other people in this area is kind of a little bit delayed because of all of the success of the large language models. But I would like to get back to this.
Okay, so it's a good place to get hybrid systems. Actually.
Yeah, that's right.
More questions?
In fact, this hybridization is important because what logic can't do very well is to tell when two sentences have roughly the same meaning. So if you want to know that two sentences mean the same thing, it's better to ask the large language model than to try to do it with logic. And the rules of logic, you have to have an exact syntactic match if you're going to use the rule, which is what's called very brittle. That means it often doesn't apply. And that's the main problem with logic in this area.
So here you mentioned in this in 42, I think, or 40, page 40, you mentioned that you have already enriched the lambda, type lambda calculus.
Yeah, do you want to know about the enriched lambda calculus? Yeah, we have yeah, we have the typed enriched, we have a lambda calculus like the simply typed lambda calculus, except that the arrow, the function space arrow in the lambda calculus is replaced by three function types: the monotone function arrow, the antitone function arrow, and the any function arrow. Because that's what I think you need to do this in a nice way. And then we have the kind of Friedman theorem that something is provable in our logic if and only if it semantically follows. So it's like a completeness theorem coming from like Friedman's theorem for the typed lambda calculus. Yeah, if anybody wants this, just let me know. We can send you stuff about this.
And what does it mean, polarize the input sentences? So you say that you have a running system that can polarize the input sentences. So does it have some relation of polarity?
No, what I mean by that is, let me see if I have it in another slide here. Hang on a second. I'll tell you what I mean. Let me stop this for a second and go over to what I mean is we have a system that you could ask it, you type a sentence and it will put in the arrows. So let's see if I have anything. I think I don't have anything open and I don't want to go through my files. We have a system that you sit at the keyboard and type in it, every dog loves 3 cats, and it will put an arrow down for the dog, and the 3 would have an equals because the meaning of numbers is a difficult story and stuff like that. So it would put in the arrows for you.
Do you do something with the inflection, with the lexical inflection, or the verbs?
No, we don't know how to do that. No. I mean, our system is fairly limited and it should be extended.
So everybody is welcome to try to
Yeah, it is. This whole thing is we're the only ones doing it, so there's a lot of open kind of areas like that.
So some more questions.
Okay, anybody can always email me questions, and I'm happy to chat with you all.
Thank you very much, Larry.
Okay, thank you all. Okay.
It's time to thank Rosanka for the organization. Very nice program also. Helping with the technicalities all the time and always being ready to do that. I say if I have forgotten someone, but that's the two that I have observed.
Okay, I hope we continue with this. It's a symposium actually. This year is the focus on proofs and verification systems. So I hope really very much that we can see better and better systems. So mathematics needs such work from young people more and more. So Larry, thank you very much again.
Okay.
And see you next year in person.
Okay, bye.
Bye bye. My best regards to everybody. My heart is there. So now I don't know what we have, but we have one more day tomorrow. Shorter day. Tomorrow is there is tomorrow the management committee, and I think that's it. Till next year. Thank you very much. So everybody gets nice talks. See you next year. It's a choice.